So I'm glad to talk here. Although I have to say I'm not really an expert on these neural networks. So everything I will say about this connection between this neural network way of thinking, or this machine learning way of thinking, and physics, I learned it from my great PhD student. Anyway, I was saying that at first sight, trying to understand many-body physics from the point of view of neural networks is the end of physics. That's exactly what we don't want. We don't want to put our physics in a black box and getting back some numbers without actually understanding the symmetries, without understanding anything. But of course, I believe very strongly that exactly the same was said like almost 80 or 90 years ago, when Monte Carlo kind of techniques came into place, and people say, ah, this is the end of physics. We will not be able to understand this because these are black box algorithms that just give us numbers. Probably we are in a little bit of the similar situation right now with these neural networks, is that for the moment it's like an amazing thing, but it's still very important to try to understand basically what it tells about physics. And my talk is really about this kind of idea. How can I understand the limitations, or basically also the benefits of doing many-body physics with neural networks? So my talk is basically trying to understand this. It's not so I will not kind of show you amazing results or ideas, but somehow it's more, you have to look at this talk as from the point of view, okay, how can I understand what is going on, what the power is, and why actually these neural networks are indeed extremely promising, but that there's also kind of strong limitations. So the overview of my talk, I will start with going back to the quite a few years to the 80s, when people were actually the first time thinking of simulating strongly correlated many-body systems, spin systems, antiferromagnets. And there were basically two completely different approaches that happened at exactly the same time. Namely, the Hughes and Elser kind of worked on this, and then there was of course the resonating valence bond state kind of way of looking at antiferromagnets. And it turns out that these two things are quite different, and one of them is very much related to the point of view of neural networks, and the other point of view is very much related to the point of view of tensor networks, which is the topic that actually I'm working on most of the time. So the whole talk is basically trying to understand the tension between this, trying to understand the advantages of one method as opposed to the other one, and trying to merge, basically trying to understand both why neural networks work so well and why actually tensor networks work well. Okay, so let me repeat what you have already heard in many talks. So I will go very quickly over this. So the quantum many-body problem. Well, I have like n spins, spin 1/2. The Hilbert space goes exponentially fast, and therefore simulating somehow such systems is basically the central problem in statistical physics, but also in quantum field theory, condensed matter, atomic physics. It's really, this is the problem that theoretical physicists have been struggling with for many years. And the reason that physics is possible at all is that we are very lucky that Hamiltonians are actually local, and that makes actually all the matrices that we have to diagonalize very special. So there are immediate kind of consequences from this locality of Hamiltonians. For example, it means that if you know the ground state of such kind of a big system, you also immediately have lots and lots of information about excited states, about the spectrum, about the entanglement spectrum, about the dispersion relations. All of this information is actually encoded in the ground state of your model. And this is extremely non-generic. If you would take a random matrix and I just give you one eigenvector, this would not tell you anything about the other eigenvectors. Well, in physics, this is very different. Just because this Hamiltonian is local, one eigenvector, namely the ground state, gives you basically information about the whole low energy spectrum of your full Hamiltonian. That's why indeed somehow we are interested, so much interested in indeed these kind of ground states of many-body systems. And of course, there's many problems that people, of many techniques that people have developed to solve the problems, but there's always some kind of problems associated to it. So typically, the typical point of view is start with Hartree-Fock, do some Feynman diagrams, perturbation theory, and make them extensive by summing infinite series of perturbation things. But of course, this remains a perturbative thing, no? And this is so there are certainly kind of systems of for very many systems this is a great thing, but also for systems that really have strong correlations, this does not work. Of course, there's the renormalization group. There's real space methods actually that don't really are compatible with this. So we don't understand how to, for example, use the renormalization group for solving the Hubbard model. There's like, especially like for field theories, there's this very kind of special kind of type of problems that have revealed lots and lots of information about the intricate kind of structure of interacting theories. Conformal field theory, the beta ansatz, Littinger liquids. These are theories that kind of revealed a tip of the iceberg of what kind of fantastic and exotic phenomena can happen whenever you have strong correlations. But typically these methods have huge limitations and actually have way too many symmetries. That's exactly why they are exactly solvable. And it's not entirely clear how to kind of deal with these things in higher dimensions. So that's certainly, as far as I understand, the biggest kind of challenge in high strongly correlated systems is really kind of the 2- and 3-dimensional strongly correlated systems to simulate them. Of course, there's lots of other computational methods like DFT, DMFT, exact diagonalization, Monte Carlo, DMRG. Now, since very recently, this neural networks. But every one of these methods still has some notion of some problem. No? Like there's, of course, like for exact diagonalization, there's the exponential wall. There's some sign problems. There's like we don't really know how to do real-time evolution with many of these methods, and so further. And what has actually helped a lot, and this is really where I'm coming from, this is the community that I'm coming from, is that this whole field of tensor networks and quantum information theory has actually provided a new perspective on several of the fundamental problems that were plaguing these traditional approaches. And the main mantra of how kind of people nowadays try to understand indeed these strongly correlated systems is basically trying to understand how you should model the entanglement degrees of freedom in these systems. Okay, so let me go now to one of the very first attempts to kind of understand or to construct wave functions that have actually an exponential number of different kind of, there's a superposition of exponentially many different kind of things. So there's an absolutely great paper of David Hughes and Veit Elser of 1988, and you will see later that at exactly the same time there was another kind of paper that tried to do the same thing but in a completely different way, and this will exactly be somehow the neural networks versus the tensor network approach. But anyway, so here you have like a wave function, and you say, let me start with some superposition of all possible configurations. So this alpha is basically the sum over alpha. This is basically all spins up and down. You just take a superposition of, it's basically a product state, because this is like a superposition of all pluses and minuses and up and down. So it's, and then you basically try to filter this wave function. This was the idea of constructing variational wave functions. Okay, so basically you kind of filter this and make sure that this H, so this Hamiltonian H, only contains diagonal terms. Okay, so it's typically a sum of sigma z's. So this is a local Hamiltonian. Maybe it contains 2-body, like in the triangular lattice, it contains 3-body terms. And you just kind of use this Hamiltonian as a filter to kind of give to give more weight to some configurations and less weight to other ones. Okay, so you take H completely as a sum of local kind of terms in your Hamiltonian, as a sum of terms. So you have like sigma IZ, sigma JZ, with a kind of depending on the distance between them. And you see with very, very few parameters, you can construct very non-trivial wave functions. So in this particular case, there's basically only, well, there's only kind of 2 parameters. There's basically this prefactor, K, and then there's basically the power sigma. And you can just optimize over these parameters and try to get kind of good wave functions. And amazingly, well, somehow they get amazingly good kind of energies by variationally optimizing like just a handful of parameters with such a method. So just to compare, like for the square lattice quantum Heisenberg antiferromagnet, they get energies of minus 0.3319 per site, and the exact, or somehow the state-of-the-art results with Monte Carlo are basically 0.3345. So you see, this is actually more accurate. This is like accurate in the order of 1%, which is great for a variational wave function that is very kind of simple. Okay, so now it turns out that actually this ansatz of Hughes and Elser can be also kind of leads, if you think a little bit further about it, is very, very kind of close to, in spirit, to the Boltzmann machines that are used kind of to simulate strongly correlated quantum systems, like what is your community is doing. So basically, this is a reformulation of what Hughes and Elster are doing. So you take this wave function, act with the exponential of something. So why do you have to act with the exponential? Why the exponential? It's because then it's kind of extensive. You want to have extensive perturbations. You just don't want to act with the Hamiltonian on your state. No, you want to work with the exponential such that it's extensive, and basically you have also the higher order kind of terms. But now there is something like a great idea that basically gives more kind of that makes this kind of idea more successful by realizing that if you start with all these product states and then you act with this exponential on this, that if you project out a few of these spins, so basically you, as you say, not all of these plus spins are basically physical, but you project some out of them, you can actually generate higher order terms. Okay, so this is a very well-known idea in quantum information. If you kind of have three kind of two-partite IDs, so all these terms commute, of course, so basically they can generate entangled states between pairs. But then if you project, so let's say you have an entangled pair here, you have an entangled pair here and here, if you project out the middle one, you can actually create genuine three-partite entanglement. Okay, so by kind of projecting out some of these spins, you can create a much richer kind of structure of such wave functions. So you start with this Hughes-Elser ansatz, you project out a few spins, and this turns out to give exactly somehow this reduced Boltzmann machine kind of ideas that have been kind of proven, that were introduced by the main organizer of this conference not so long ago. But this is just a way of understanding somehow these things. So you start from this Hughes-Elser ansatz and project out a few kind of these spins, and this is exactly equivalent somehow to some reduced Boltzmann machine way of parameterizing these systems. Okay, so what is this would be somehow these two-body interactions. So you have all these lines, and then basically you project the hidden units out. This is just kind of projecting them out on the plus state, and then you end up with another state. So if you would write this out explicitly, start with this Hughes-Elser ansatz, project this out, you will see that indeed I can write this as an exponential of a log of a cosine hyperbolicus and so further. And if you kind of expand this in a Taylor series, you see that indeed you don't only get two-body terms, but also four-body terms, six-body terms, eight-body terms. So in many ways, somehow this ansatz of reduced Boltzmann machines for quantum many-body states is like resumming infinite series of these Hughes-Elser kind of things, and you get indeed these higher order terms because of the projecting out that they generate indeed this higher order kind of types of entanglement. And indeed, by doing this, you still have, well, you kind of have lots of you have, of course, kind of in this particular case for these Boltzmann machines, more parameters, but still not that many parameters. And indeed, you get kind of, you gain an order of magnitude in precision by doing this. And actually, the way you optimize these wave functions, whether you project this or not, is completely equivalent to the way you optimize the original kind of Hughes-Elser ansatz. So in that respect, it's still somehow a variational Monte Carlo method, but somehow the big advantage is instead of having only kind of two-body terms or three-body, you actually also you generate the higher body terms because of the projection that you are doing. Okay, so these neural networks actually it was then proven by many people. So this was like, as you all know, a huge kind of this led to a huge kind of excitement in the field, and people wanted to understand this. And indeed, you can also understand this from the point of view of tensor networks. Actually, there were some ansatzes that were introduced by Norbert Schuch and Ignacio and myself, and then in this paper of Ivan Glasser and company and co-authors, they realized that actually also these reduced Boltzmann machines can be understood as string bond states. So there's lots of interesting kind of connections between those things. But nevertheless, there is, well, there's certainly some kind of open questions. What happens with this? What is the specificity with respect to as a function of the polynomial number of variables? It's clear that entanglement is not the bottleneck. But what about kind of much more complicated methods, no? Like the Hubbard model, Verstraete magnets? Of course, people have kind of, there's lots of works on this, but I think this is, the jury is still out whether, for what models these kind of machines can be used. But from my point of view, what I disliked or kind of did not find very natural is that both this Hughes-Elser as the restricted Boltzmann machines as the string bond states, that they all share that one kind of very unphysical property, namely that you always have to start from a given basis, from a certain basis. So all the results, so by that means because you must have some classical basis like an up and a down spin. And then you kind of sample in that basis, but that's the choice of the basis you made somehow will always follow you in all your kind of optimizations and everything that you will do. So in many ways, so you get results that are biased towards the diagonal basis. So in some sense, you're kind of trying an answer that is maybe too classical for simulating some of the more interesting kind of quantum many-body systems. And certainly, if you want to simulate spin liquids that that do not break any SU2 symmetry, it's completely unclear how to enforce that, how to kind of write down a restricted Boltzmann machine kind of that has SU2 symmetry. Of course, there's more complicated models that allow this, but I will for this talk kind of restrict myself to these restricted Boltzmann machines. Okay, so so let me now kind of move to some other kind of development that happened at exactly the same time as this kind of Hughes-Elser. So this was kind of, I think the paper of Hughes-Elser was February 1988. Well, this paper, very famous paper of Liang, Dussault, and Anderson was 1988. So this was actually a competing paper in which they also tried to kind of guess or find some kind of a nice way of writing down the wave function of the ground state of the Heisenberg antiferromagnet. Okay, so, but the philosophy there is completely different. So they don't start with the plus state and apply some diagonal filtering operation, because that's what this Hughes-Elser and other methods do. So here you start explicitly from singlets. So what you basically do is this resonating valence bond state. So what you do is basically write down your wave function as a superposition over all possible singlet configurations. Okay, so you kind of take a singlet between spin I1 and J1 and IN and JN. This is because it's a bipartite lattice. You can always kind of make sure that they don't mix these singlets. And then you give them some weight. Your wave function is just some kind of a weight function depending on all these kind of quantities. So what is the big advantage of this wave function, or of this way of parameterizing the ground state of the Heisenberg interferomagnet, is that you automatically have your symmetry. So you automatically have your SU2 invariance encoded, because I1, J1 is a singlet, and a singlet is, of course, invariant under SU2 kind of symmetries, under global SU2 rotations, and every one of these singlets is like that, and therefore the global wave function psi, also inherits all these properties. It turns out that actually you gain an order of magnitude in energy by indeed enforcing this. Okay, and so the starting work actually with the student Tom Vieira was exactly was very, very much motivated by that. You see that actually SU2 invariance is very important, because if you compare somehow the success of these methods, they have the similar amount of variational parameters, but nevertheless, if you enforce somehow SU2 symmetry, you can gain a lot. And it turns out this has been investigated by Clark in a very nice paper, that indeed kind of writing down wave functions with reduced Boltzmann machines that have this SU2 symmetries seem to be problematic. It's not easy at all to kind of write them down, and you need several layers, and then the optimization becomes problematic and so further. Okay, so this resonating valence bond states actually are very, very close in spirit to what we do in tensor networks. So, what I want to show here is that basically tensor networks do something very, very similar to what you did in the neural networks. Namely, you say, well, I start with some configuration with some entangled states that have like, well, some very simple type of entanglement, or some product states like in the reduced Boltzmann machine. And then actually the power came from projecting out things. So first you filter, and then you project out some of these states. Well, this is exactly what happens in somehow all these tensor networks. So there is a simple way of understanding tensor networks in terms of starting with singlets. So for example, this blue dot's connected by this wiggly line. This is a singlet. This would be another singlet, and so further. And then you say, well, let me project these kind of things down, but not on a diagonal basis, but in a basis that respects the SU2 invariance. Okay, so this is actually what the original AKLT people did to construct the spin 1 Heisenberg chain, and of course it's much easier to kind of generalize this to much more general kind of constructions. And this is exactly what these tensor networks do. They start also from a very simple state, but instead of projecting this down on a diagonal basis, you project this down on a very non-diagonal basis. But the price you have to pay is that you have to kind of keep these things much more local. Okay, so these tensor networks, so this is basically, in a very nutshell, this would be the history of tensor networks. So AKLT people, they introduced this amazing kind of state for proving some mathematical theorem. Then von Nachtergaal and Werner, also three kind of mathematical physicists, kind of generalized this kind of things. And what they basically realized is that these matrix product states have a beautiful kind of theoretical properties that can lead to a big understanding of a nice understanding of quantum spin chains. This is basically all mathematical work, but then there was also numerical work, both by Kenneth Wilson and Steve White, who was his student, kind of realizing that the structure of matrix product states is extremely useful to understand things. And then in 2004, together with Ignacio Cirac and Guy Vidal, we realized actually that quantum information tools give you exactly the right kind of language for understanding why these methods are so kind of, these numerical methods are so useful, and how kind of to put much more structure and understanding somehow the reason why we need this and this and this answers for these different models. So indeed, somehow these RVB states of Anderson, they have a very simple representation in terms of these matrix product states, or these PEP states in this particular case. It's a projected entangled pair state. There's a very simple way of doing this, writing down, for example, the superposition of all possible singlets with just nearest neighbor interactions. Well, you can do this with bond dimension 3, and this gives you this RVB state. And the nice thing is that they are completely basis independent. No? So they have the symmetry, but also, and this is the reason that I personally am so excited about tensor networks, is also they kind of contain lots of beautiful theory. So because of writing down this wave function, you can start understanding lots of the structure there. You can start understanding what the acceptations are. You can start understanding that indeed there is some hidden non-local symmetries in these states that are actually very explicit if you look at them from the entanglement point of view. So basically these tensor networks are an explicit implementation of all these ideas of the holographic principle, that there's an extra dimension in which you can look and understand the physics in a much easier kind of way. And well, this is certainly, there's lots of work being done on that in that sense. But anyway, so this is so the tensor network point of view is actually in many ways the implementation of Anderson's ID and generalizing this to not just RVBs, but to much more general classes of problems, while in many ways all these neural network kind of methods are much more in the spirit of Hughes and Elster, in which you only filter in a diagonal kind of way. Again, that's why, of course, the natural thing to do, and this is where Tom Vieira, and actually Tom is the one who did all the work here, how he, so we wanted to merge these two approaches. We wanted to see, is it actually possible to come up with Boltzmann machines that actually also inherit these SU2 symmetries? And at first, this was not completely easy, because of course, if you sample your spins, but then we realized actually that you don't want to really sample the spins. So what you want to do instead is use somehow the tensor network language to write down a wave function or in a certain kind of basis, but this basis is now a basis of EREPs. And so I don't have enough time to really explain how this kind of works in detail, but somehow the tensors that consist of this tensor network all consist of Clebsch-Gordon coefficients. So if you want of 3J kind of Wigner symbols, they are all, of course, very much related to this. And the degrees of freedom, as you use somehow the symmetries in tensor network language for describing a wave function, the degrees of freedom are not at all the spins, but the EREP labels. So the labels of the irreducible representations that are present in your kind of system. And of course, these EREP labels, they have a preferred basis, okay? Because of course, superpositions of EREPs is something that is not very natural, but the EREPs themselves have kind of, or have a very, very clear kind of meaning, even in quantum mechanics. So this EREP basis is a much more classical object than the spin basis. And so what Tom kind of implemented in some very nice work is that you can actually put somehow now a restricted Boltzmann machine exactly on top of these EREPs where your degrees of freedom are not the spins, but the EREP labels, the irreducible representations labels of your kind of many-body system. And indeed, somehow, if you start doing this and you start applying this to spin 1/2 or spin 1 Heisenberg antiferromagnets, you see that actually with much less effort and like the ratio m divided by n is the ratio of kind of the number of hidden spins versus the number of physical spins. You kind of have a much there's a much more efficient way of kind of getting good energy. So this is actually the blue curve is this new method where you use symmetries. The orange curve is actually the when you sample in the sigma z basis, so like in the Hughes-Elser kind of ansatz. So this is the error in the energy. This is the variance basically of your state, of the ground state that you get, and this is basically the fidelity that you get as a function of the ground state. Okay, so we were very excited. We thought, okay, well, this is the best of both worlds, no? So now we can use these EREPs using tensor networks to basically find the middle ground between this Anderson kind of approach that is very nice, but is not so kind of intuitive and is actually not so easy to reformulate in terms of these Boltzmann machines, and the Hughes-Elser kind of ideas that are really exactly kind of completely in spirit of the reduced Boltzmann machines. But then somehow after that we realized that that's actually not so easy. So like in the recent kind of year, we have been looking at things like the square lattice J1 J2 model on 4x4 sides with periodic boundary conditions, and in principle these wave functions with symmetries are exactly able to represent the ground states of such models. But the problem that we have, and this was certainly not expected at all, is that the problem that we have in finding these representations in terms of these SU2 invariant restricted Boltzmann machines is in the sampling. So if we just sample, even if you kind of take 100,000 samples, and for a 4x4 site that is a lot, your energy, so this is the green, and somehow these curves on top here, these are the ones when you kind of use stochastic sampling methods for kind of guessing the gradient and then optimizing your restricted Boltzmann machine. It just does not work. And what Tom realized is if you kind of just use the exact gradient and you optimize basically your parameters of your restricted Boltzmann machine with somehow using the exact gradient, then it works perfectly. So it does not seem to be even a problem that these restricted Boltzmann machines cannot kind of capture the physics of your kind of system, but the problem seems to be that you cannot optimize easily over them, okay? Because of course this is kind of a Hilbert space that is exponentially large, so there's no, you could do it here, you could calculate the exact gradients because it's only 4x4 sites, but if you have, like, you want to do this on a big system, there's no way this can be done exactly the gradients. You have to sample them, and there seems to be some kind of completely ununderstood restriction of sampling how to kind of deal with this problem.
Frank, well, 5 minutes.
Yeah, okay, that's perfect, because I have just in the last part of my talk. So let's kind of try to dig a little bit deeper into the reasons why indeed it's so important to this basis dependence or basis independence is actually an important kind of issue. Okay, so let's so in many ways the way I understand this Hughes-Elser ansatz, and therefore also somehow this restricted Boltzmann machine kind of approach, is that this is very much like actually an extensive perturbative expansion. Okay, so let's assume that you start with only the term, this is for an Ising model. You start with the sum I xi, and then the ground state of that is exactly the state that you started with, the plus state, the superposition of all possible states. And you treat basically this lambda 1 zz as a perturbative kind of perturbation of your kind of ground state. And then you would like to know, how do I write down my wave function as a function of somehow this lambda? Well, if you do this kind of first and second and so further order perturbation theory, you get exactly this ansatz of Hughes and Elser. Okay, so this is somehow the extensive way of doing perturbation theory on top of somehow for the Ising model would exactly give this kind of wave functions that you expect. Okay, and indeed for this particular case, what is very nice is that all these terms actually commute. Okay, so because the perturbation only involves sigma ci cj, so there's no other kind of terms here. Everything commutes just as somehow in the restricted Boltzmann machine kind of ansatz. But of course, this means that it will work very well close to somehow your classical state or your state that is a superposition of everything. But there will be kind of much more problems once you kind of go to a phase transition. And actually, you also want to kind of get contributions of the other terms of your Hamiltonian. Okay, so so what you want is that this kind of, if you kind of look at this exponential here of this h, you do not only want sigma z terms, but you also want plus terms, and this is very important. You can actually understand this from the point of view of the quantum wave function. Once you kind of are far enough from somehow your ground state of your product state, you will need somehow the you will need to kind of take into account the fact that the terms in your Hamiltonian don't commute. So you want to take into account also kind of terms here that like x terms, y terms, z terms, and you need kind of all of those to kind of get a faithful kind of approximation of what happens, not just close to the to somehow your product state, but also kind of far deep in the regime of strong correlations. Okay, and somehow a year before Tom started working on this, and actually also very recent, we had been kind of thinking a lot about kind of such expansions. How can you deal with this? What is the more natural way? And it turns out that these perturbative expansions gives you a very kind of very simple kind of way of parameterizing matrix product states or PEPs wave functions that allow you to kind of get this. So what is this? So in many ways, so what we realized in these papers is that PEPs and matrix product states and tensor networks are very much in the spirit of this huge Elser ansatz, but you also allow for non-diagonal terms. You now allow for non-diagonal terms and non-commuting terms, and exactly these terms are the ones that gives you somehow an extra kind of power. And you can do this exactly. For example, you start with this, and then you say, okay, for example, this is you start working with matrix product operators or projected entangled pair operators. Sorry for the people that have never heard of this, but anyway, so these tensors, this exponential becomes basically a combination of z terms and x terms and so further. And if you do this, you get actually an amazing kind of nice, kind of a very powerful way of not just kind of doing the physics close to your perturbative expansion, but also far away from it, even kind of crossing a phase transition. And these were some kind of plots in this paper that Lawrence van der Straten kind of pioneered this kind of whole approach, in which we even kind of come up with ordered parameters for topological phases and so further. But anyway, so there's of course a price we have to pay. Okay, so this seems so that means the tensor networks are in many ways similar to the neural networks, but in which somehow you take quantum Hamiltonians instead of classical Hamiltonians to give weights to the distributions. But of course, this non-commutativity also has like lots of problems, and therefore we can actually only take local terms. Okay, and it's really kind of a tension between this. That the question, the jury is still out, which one of the two kind of is better, and certainly for some cases this is better, for other cases the neural networks will be better. We don't really kind of know beforehand. But anyway, so the criticism that I always hear, or somehow the selling point for these neural networks, as saying, okay, they have to be much better than these tensor networks, is always, well, we can kind of deal with lots of entanglement. We can kind of deal with wave functions that have much more entanglement than you can deal with in tensor networks. But I just wanted to add that this is actually completely unfair. So it's also very easy in terms of tensor networks, for example, in PEPs wave functions, to kind of come up with wave functions that have arbitrary amounts of entanglement. So for example, if you have a PEPs wave function here, what you can do is just make only very few of somehow these tensors physical. You only put a physical leg on very few of these tensors. And then of course, all these kind of other mediating tensors, they actually also kind of can distribute entanglement, and you can put as many as you want. You can still contract this efficiently using somehow tensor network techniques, and you can also kind of get as much entanglement as you want. And actually, if you think a little bit about this, this is actually a very similar way in which somehow you can understand also Laughlin states, these chiral states, and so further. So we're actually writing, we'll kind of write a paper on kind of things like that soon. So I just wanted to counter this because I know that people, that's the first thing they will tell me after this talk. They will say, yeah, tensor networks are not good because they don't have like, they don't have enough entanglement. I don't think this is a fair criticism at all. But anyway, I think it's time to stop here. So I think the way I understand, so I wanted to, so this talk is really about my way of trying to understand why neural networks, how they work, what are they good for, and how kind of do they fit in the traditional approaches that people have been kind of working on. And so there were kind of clearly two kind of approaches that I stressed: the Hughes-Elster approach, that is very, very close, also the way you kind of simulate this to these neural networks or the restricted Boltzmann machines. The nice thing, the really nice thing is of the additional kind of power that you get from the Boltzmann machines is actually the fact that you have genuine multi-parted entanglement. And I don't think this was completely appreciated in the community, that this is a very important kind of feature. But of course, the reason that we also started working on this is that I really want to understand to what extent it was possible to overcome somehow the basis dependence. The fact that you work in a specific computational basis, to me, looks like something very non-quantum. So you don't want to have basis dependence in your kind of variational ansatz. So certainly, if you want to simulate spin liquids and you already have a preferred basis, then of course you will never kind of be able to judge whether this is a spin liquid or not, because a spin liquid should never kind of break any symmetries. And somehow I try to kind of understand and indeed seeing that indeed these tensor networks and these Boltzmann machines and actually these neural networks, they are very, very much related. And I think this is maybe just a starting point. I'm trying to understand somehow these problems, and I think this is really what is one of the things that is really needed. Trying to understand indeed the limitations, the power. That's exactly what all of you are doing, and that's why this conference is such an exciting thing. So I just want to end with a cartoon. This is Goliath. This is David, or the opposite, actually. No, well, you know which one is David and Goliath. One of them is tensor networks. The other one is the brute force kind of neural network approach. And let's kind of start a big battle. Thanks for your attention.